Now for this tutorial, I want to again tie together our knowledge. I think we understand we're always asking three questions. We're asking what type of data are we working with? We're asking where is the center of this data, and where finally the third question is how spread out is the data? Okay, and so we have different ways of exploring how that works, and one of those ways is with box plots. And so if I've got the data is 1, 2, 3, and 6, with a box plot, I know my minimum value is 1 and the maximum is 6. So I can begin constructing a box plot here, and the middle is in here, so that's 2.5. So we've got Q1, the minimum, maximum, and Q3. Now that's going to be halfway through between those 2 points, so that's got to be 4.5, and this has got to be halfway between here, so it's got to be 1.5. So what we know from there is 50%. 50% of the data is inside the box, and tick, we can see that. Okay, both the values of 2 and 3 are inside that box. Okay, and that's essentially what we're doing when we're doing box plots. We're finding the middle and we're checking out how spread out the data are. So there's another way we can do this, and it's using the normal distribution. And to do this, we need to look at how the data are distributed on the normal curve. Okay, so in the middle, my rough drawing, my bad drawing, but in the middle we have the mean of the sample, and what we measure here is plus or minus 1 standard deviation. So subtract a standard deviation, and here we're going to add a standard deviation. And we know that if I try and draw this a little bit better, a little bit more symmetrical, we know that we know a couple of things. We know 50% of the data are either side of the mean, and we know plus or minus 1 standard deviation. We'll get approximately 68% of the data falling either side of the mean here. So that's what we need to calculate, and often we do that. We calculate the mean plus or minus 1 standard deviation. So what's becoming important now is that we need to understand a little bit more about this standard deviation. And what I want to do in this tutorial is use this formula that's been presented to you, and unpack that a little bit. Now, I want to reassure you along this video that you can quickly jump onto your calculator and calculate this value without knowing anything more than what I've just told you here. But along the journey, what I want to do is help you understand how the notation works and actually what it's doing, because we'll get on to another question where that kind of understanding, if you know what's going on, you get a sense for how the question's going to roll out, and get a really good sense of what's happening in the situation when we come down here and we look at this question here where a chemistry student has performed an experiment and accidentally wrote down the wrong value here. So that's where we'll get to. But right now we need to understand a little bit more about the mechanics of calculating a mean and a standard deviation. So we're going to do that, and we're going to write down the mean, or x bar, which is the sum of the x values divided by the number of data points that we have. Now, our data set was 1, 2, 3, and 6. So we could do this. Perhaps we could do this by hand. The sum of just literally means for the man on the street, just add all the numbers together. Now, it's a small data set, so it's not a difficult job to do. So we've got 12 divided by 4 here. And that's going to be equal to 3.0. Okay. So what we need to do now is work out the standard deviation of the sample. Okay. And the formula that was given there was kind of the same symbols appear. This is a sum of x being the individual data point subtracted from the mean, which is what we had here. And then we're going to square it. And there's a little bit deeper understanding here, but because it's the standard deviation of the sample, it's a bit more of a conservative measurement. So we're going to take the number of data points and subtract 1 from that. Now, how does that look? And it might be worth writing it out, but not necessarily doing the calculation, because that might get a bit crunchy and grindy, and just you need to know now that it's really rare that you'll be actually asked to do this calculation, but you need to understand it. So what do we got? We've got 1, our first data point, subtracted from 3, and then we're going to square that. We're going to take the second data point here, and we're going to subtract it from the mean, which is 3. We're going to square it. And now we look at the third data point, which is a 3, which happens to be our mean. And we're going to subtract that by 3. And that's good news, because that's going to cancel to 0 and save us a little bit of work. Now we've got 6 subtract 3, and we're going to square that. Now we had 4 data points, subtract 1. So that's going to be 3 as well. And let's do the next little bit just to show you where this is going. So our denominator is 3. Let's come back in here. 1 subtract 3 is -2, and we're going to square that. And we've got 2 subtract 3 is, we're going to add that, -1 squared. The middle, this one here cancelled out, so we've got 6 subtract 3, and we're going to square that. That's a +3, by the way. And this is important because now I'm looking at those negative signs, and now I'm thinking about, well, -2 times -2, we have a negative times a negative, and the answer is going to be positive. Okay, so that's going to be +4. And so this stuff looks like 4 plus 1 plus 9 over 3. Okay. So what's happened there is all the negatives, by squaring the those little calculations, we've dispensed with having negative signs, and that's tricky because we don't want to end up with a negative sign under the square root here, because we'd need to use another branch of mathematics, and we'd have to use complex numbers to find solutions to that. And so essentially what do we end up here with is the square root of 14 over 3. So there's a calculation, and we've got that far. But it's worth doing it on the calculator, I think. It's much more easier. And the things I want to show you okay? You can type this in. If you wanted to know the mean, we can do this. We can use the curly brackets there and write out numbers in a list separated by a comma. Close the curly brackets and close all the brackets and enter on that. For the same reason, I keep saying the standard deviation of the sample. And same thing, if you type that in, it's a function inside the calculator, and we can do this and make our list. Close the curly brackets, close the other brackets, and see what we get. Perhaps I typed that in wrong. I think I did. So I've ST for standard deviation, so DV and sample. Maybe I did that wrong, but I can quickly try this one out and see if I've got it right this time. Close the brackets and let's go. What we need to do there, because it's in, my calculator is in exact mode, I can just wrap all that in approximate and I'll get my answer here. Again, closing the brackets, another bracket this time. And I should get something that's a bit more meaningful to us. So now what we can write here, having done these calculations, is we've got the mean is 3 and the standard deviation of the sample is 2.16. So to answer these questions, what we need to come back to and think about now is writing this to answer this question. And it was question 2, I think it was. The mean was 3.0 plus or minus 2 point, now I've forgotten the numbers, 16. Let's do this, 2.2, let's round it up to the 1 decimal place. So essentially what is that saying is that our mean was here at 3, and I know it's a very small sample. We've got mean is equal to 3, and we're saying here plus or minus 1 standard deviation, which would be subtract a standard deviation. So this value here, I might ditch that, would be 3 subtract 2.2, so 0.8. And this value here would be 3 plus 2.2, so we're at 5.2. We're saying 68% of the data should lie between these two points here. So we've only got a really small sample, so to see that better would need a larger data set. But for the purpose of giving you that demonstration, it's good just to play around with some small numbers here. And we might return to this shortly. So what I think is a good thing to do now is just show you some other moves. Like we could have done it this way, and we could have come in here and put a lists and spreadsheets page in here, and on our calculator we would have got those values quite quickly just by going stat calculation, and let's try that again. Menu, stats, one variable, statistics. Now I feel like we've done this a few times, and so this should be quite automatic for you. Now we're just checking that we've got the right thing in here. Yes. So here's our mean, and we can read off the value. And this one here, that's why I wrote SX, because this is the standard deviation of the sample. And it is a larger number than the standard deviation of the population. Can you see how the symbols are different there? And the standard deviation of the population requires everything to be measured. So it's always going to be a smaller number. So the standard deviation of the sample is a more conservative value, and it's setting, what it's actually doing is setting these these lines here out a little bit wider, and that's what I mean by being more conservative. Okay, and there's only one small difference in the calculation, and that difference is here in here. Instead of being n minus 1, if we want the standard deviation of the population, everything is the same except it looks like this, divided by n, because we've sampled everything in the population. So that's above and beyond, but that helps you understand, and hopefully helps you understand to be mindful and choose the right number here, because they're sitting one underneath the other, and we need to know why they're different, and so it's worth pointing that out to you. Let's have a look here. We've got this situation here where the chemistry student has been recording some results, and we need to find the mean and the median, because we want to know where the center is, and we want the interquartile range and the standard deviation of those results as well, because we want to answer that other question about the spread of the data. And the interesting thing that's happening here is that the student has made an error and wrote 60 instead of 6.0. And we want to try and understand what effect that's going to have on the summary statistics that we're collecting. Will it have a big effect on the mean? Will it have an effect on the median? And that's what we want to know. And as we build our understanding, we probably want to come over here and start thinking about putting those lists in order. And let's do that quickly now. We've got 5.9, we've got 6.0, 6.1, 6.2, cross them off as I go, and I missed one. I've got 5.8. I'm going to stick it out here, 5.8. And now what have I got on my list? 7.3, 7.4, another 7.4, and an 8.3. Double checking. I got one of those, two of those, two of those, and finally one of those. So how many data points have I got? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's handy because n is equal to 9. So the middle will be n plus 1 over 2, and that will be 10 over 2, sorry, not 10 over 5, because I've thought about the answer, and that's the fifth data point. So count in, 1, 2, 3, 4, 5. Here's our median. Okay, so on this other set of data, everything else is the same, except down the other end we've got a 60. So 5.8, 5.9. We haven't got a 6, but we've got a 6.1, a 6.2, a 7.3, 7.4, running out of room, 7.4, and 8.3, and a 60. Okay, so our calculations are the same. We've still got 9 data points here, 3, 6, 9. And the fifth one, 1, 2, 3, 4, 5, is going to be our new median. So the effect on the median was quite small. Okay, it's increased by 1.2. Okay, having this value out here, which is obviously an outlier, and an error that we would either change or have to discard as a data point. So the median has, if the difference there between the two is 1.2, and it was originally, let's round it off to 6. So maybe that's a 20% increase. Okay. 0.6 being 10%. 10%. Okay. So a little change, but because these are small numbers, that turns in percentage-wise, that is still a big increase. But let's think about what that's going to do to the median. I mean, the mean and the standard deviation of the sample. So I could do those calculations quickly and answer those just by ordering those lists and thinking about what was happening with the median. I could arrive at some answers for that quite quickly. But what I suggest now is that here you'll need to jump on your calculator, because the data crunching is best handled by the calculator, not taking half an hour to calculate these things. So what have I done here? I have put the two lists together as I haven't ordered them, but I've just put the values here. So one's got 6 and the other's got 60. So I've called that the error in the data here. So quite quickly, I'm going to do this. I'm going to go menu, statistics, stat calculation, one variable statistic. I've got two lists here. And my first list is the chemical experiment, the chemistry experiment. And my second list here is the data containing the error. So I'll hit OK on that. And we've got those two things side by side now. And we can make a really quick comparison about what effect one data point, instead of being 6, it's 60. So that's a 10-fold increase in the value of that data point. And I'm just double checking that everything's returned to the right spot, and it has. So what in effect has it done to the mean? It's doubled the mean. It's skewed the data and skewed it out to the right and dragged the mean out with it. And it's doubled the value of the mean, that one error. So now we're looking at the standard deviation of the sample, and it was quite small, and now it's I'm going to call that 0.9, and 9 times 2 is 18. So this represents roughly speaking a 20 times increase in the standard deviation. So now, to wrap up the final part of this video, we're focusing in on the error that was made in this chemistry experiment and what effect that's having on the summary statistics. Okay. And I just want to focus in on the standard deviation, because the main focus of this video was to talk about the standard deviation. And I said right at the start that there'll be something at the end that hopefully helps us understand what the calculation is doing and what effect that I guess outliers are having on the data and what it can do. So we saw that it doubled the value of the mean. So without the error in there, everything looks pretty good. We've got the mean in the middle of the distribution, and we've got a measurement. The standard deviation gives us a measurement of how spread out the data are. And we know we know that 68% of all the data values should lie within plus or minus 1 standard deviation of the mean. So we went into this situation here where we've got the mean doubled in values, so roughly, so 12.7, and we had a standard deviation of close to 18. So I think that was 17.8. Okay, and we said that was a 20 times increase in the value of the standard deviation, and that was quite large. And what does that look like? We've got the mean here. Let's add roughly 18 to that, and we're at 31. We're close to 31. Okay, on the other side, subtract 17 from 12, and we're beyond past zero. Okay, so plus or minus 1 standard deviation here is all this data. Okay, which includes most things, right? It just doesn't include this point out here at 60. So in this case, plus or minus 1 standard deviation is nearly all the data. Okay, so it's had a massive effect, and I think the key thing to understand here is why has it done that? And it comes back to the formula. So let's look at the formula for the standard deviation and get some sense of what this formula is doing. And that's why I've set this question, and that's why I've focused in on this question. And here's a formula, and let's for a moment just think about the mean. And it could be any data point, and it could be a certain distance from the mean, either side of the mean. And so when we measure that distance, the part of the formula here that we're using is x minus the mean. Okay, and then we square it. So, and I really like this explanation because suddenly we're dealing with some geometry, and it's a bit easier for us to understand what's going on. We've created this square. Not only did that deal with any situation where we had a negative, as I explained before, but with the square, we've got some sort of, I guess, for me at least, is a better understanding of what's happening here. And so we sum up all those squares. Whatever that distance it is from the mean, we create a square and we sum it up. So that's what that symbol sum of means. Now, then we've got a point that's a long way away from the mean out here at 60. And so what happens here is we create a massive big square. And that is going to have an effect on, once we sum all those squares, and that's that part of the formula, and then we average all those squares, and we that's where we do this bit here, n minus 1. Because of this guy down here, we've still got a very large average size square. Okay, then finally we're taking the square root of that. And when we take the square root of it, we bring that back to a one-dimensional distance. And being a square, we all know that all the sides of the square are the same length. And so when we bring that back to our set of data and put it here as a measurement of how spread out the data are, well, this one point out here has had a massive big effect on the sum of all the squares, and it's created a very large average size square. And so that's the explanation of why we have why we're in this situation. Now, I understand that might be a bit of a sort of next level explanation about what's happening, but I think it's really important for you to, like I said at the start of the video, start to understand the formulas, start to understand the notation and what's happening behind the scenes, if you like, and why we do the things that we do. So on that note, I'll wrap this tutorial up. And if you got this far, then thanks for listening.